Hello students, we are continuing with chapter 2 and we're looking at acids and bases. You guys are going to be able to predict which direction a reaction lies based on pKa values. And then also, this is an important area because in the future you guys are going to have to select specific acids or bases to be able to run a certain reaction. So I want you to pay particular attention to pKa in relation to whether a reaction is going to occur or which direction it lies, and then identify what whether an organic compound is an acid or base. That's going to be key for you guys. So let's just talk about Bronsted and Lowry acids bases first. These are proton donors or acceptors. You guys are familiar with this. Here's a classic HCl and water reaction, giving Cl- as your conjugate base and hydronium ion as your conjugate acid. In that sort of reaction, we use Ka to measure acid strength. And so the Ka in a classic reaction of a generic acid, HA, is hydronium times the conjugate base over the concentration of the acid itself. So we're going to be looking more at pKa in organic chemistry, which is just the minus log of that. Shown here, stronger acids will have a smaller pKa. Weaker acids will have a larger pKa. So we are going to be able to use pKa values, and you guys will get a sense for what those numbers are to determine whether certain reactions occur. So here's just a general scale. I'm going to show a weaker acid on top and stronger acid on bottom. The pKa here for HCl, strong acid, is negative. Water, 15.7, ethanol, even weaker, 16. There are way weaker ones. Up into pKa of 50 even. So this is just a kind of the lower end of the scale. What I want to show you is also the conjugate base here. So for ethanol, it's ethoxide. Notice the weaker the acid, the stronger the base. The stronger the acid, the weaker the base. Hopefully that makes sense. A strong acid wants to give up its H+, so it's happy. Cl- is pretty stable. The more stable the conjugate base, the weaker it is, and the more stable the conjugate base, it came from a strong acid. That'll be a common theme. How do you predict acid-base reactions from pKa values? So the easier way to think about this is the stronger the acid, so the lower the pKa, the more it wants to give up its proton. So this is the situation. You have two guys competing for a proton, for example. Say you have acetic acid that has a proton, you have hydroxide ion that if it grabs that proton, it becomes water. So you know reactions are reversible. Is it going to lie more to the left or more to the right? And so you need to look at what the pKa of the corresponding acids are. So here on the left, I have acetic acid that's in its acid form. That's a weak acid by normal standards compared to HCl, but we're not comparing it to HCl. So let's just focus on the pKa. pKa is 4.76. If you want to compare that and see if hydroxide is going to grab that H, you need to look at hydroxide in its acid form. So you can then write the reaction where it becomes water, and the pKa of water is almost 16. So again, the lower the pKa, the stronger the acid. It wants to give up its H+ more, so it'll lie to the side where the stronger acid has given up its H+ and it's in its conjugate base form. Another way that I like to remember it is thinking the higher the pKa wants to have or hold on to the proton. So the higher the pKa has the proton, H and H. Let's practice this. So, will the following reaction take place to a significant extent as written according to the data in the previous table? So I gave you the data, here are the pKa values. You have HCN and sodium acetate. If the acetate grabs the H and basically deprotonates, you get cyanide and acetic acid. So to answer this, you need to look at the acid forms, look at the pKa. Why don't you guys pause and write your answer to this? And you can see that the stronger acid is acetic acid here. And so it'll want to lie to the side where it's in its conjugate base form. It had given up its H+. Also here, HCN, it has a higher pKa, so it wants to hold on to its H. So it should lie to the left. So will it take place to a significant extent going to the right? The answer is no, it will not. Okay, we now get to move into organic acids. Recognize these. Here are some organic acids. Alcohols, methanol specifically with an OH. You can give off this give up this proton here, the H of methanol. pKa is similar to water. Acetic acid is one. Look at this group. This is called a carboxylic acid. It's like an alcohol, but it has a CO double bond. That's going to make that H more acidic, easier to pull off. This one is a carbonyl group here, and when you don't have an actual OH or NH or SH, and you only have CH, CHs are generally hard to pull off, hard to deprotonate the H, but if it's next to something that's going to draw electrons away, like this carbonyl group, then that can make that more acidic. So these are some very, very common organic acids. Again, in more detail, if I take two main kinds, a hydrogen bonded to an electronegative O, the alcohol, when you deprotonate, you get O minus. So if this is methanol, this is called methoxide. The reason why this occurs is because the electronegative O stabilizes that negative charge. So the whole thing about being an acid is you'll be a stronger acid if your conjugate base can be stabilized. Here, if I pull off the H+, I could get from a carboxylic acid to a carboxylate, and this negative charge is stabilized by resonance. Not only does it have the electronegative O that it's on, but this negative charge could be spread out throughout. The next is this H, the third one that I showed you on the previous slide. You can deprotonate this H and give the carbanion ion, a C with a lone pair and a minus charge. This is also stabilized by resonance. We practiced one resonance structure where you could draw a double bond and kick up this pi bond to a lone pair. This is stabilized here. So these are three common things that you'll see. Let's talk about bases. Basically anything with a lone pair is a base. So nitrogen containing compounds, oxygen, here, methanol. So notice, methanol can act as an acid or base, depending on what's nearby. Also, this acetone structure, this is used, for example, in nail polish. The lone pair is on the O here. There's another definition of an acid and base, and that's called the Lewis acid or base. Lewis acids can accept an electron pair. Lewis bases are electron pair donors. So here's an example of a Lewis base, something with a lone pair. And we've seen this, for example, N with the lone pair, ammonia reacting with borane, BH3, a vacant orbital, and you can form this new bond. This can also include metals. Sometimes you'll see that. So Mg2+ is also defined as a Lewis acid. So you can get a base and coordinate the lone pairs to that metal complexes. The group 3 elements, these are Lewis acids just because they have 6 electrons and can accept 2 more. some other transition metals as well. Let's do a concept check. Using curved arrow notation, draw the reaction of aluminum trichloride or aluminum chloride with dimethyl ether, shown here. It's an ether because it has an oxygen and connected to two C's. Don't forget formal charges. So pause this, take out your pen and paper or pencil, and draw this. Draw the structures, use curved arrow notation. And I'm going to go over it. So what you should have come up with is a structure like this. You could have written the methyl, that's fine, but two lone pairs. And one of the lone pairs, that's where the arrow originates from, and will attack the aluminum. Attack is basically form a bond. So you're going to form a new O aluminum bond. Notice the formal charges. The oxygen's lone pair is now being shared as a bond, so it gets a +1 charge. It has 3 bonds in a lone pair. And the aluminum now has 2 more electrons than it would normally have, so it has a -1 formal charge. You can use the formula as well. Notice, just for fun, you go from something with a tetrahedral arrangement or a shape of a bent shape for an O to something trigonal pyramidal. And then the aluminum chloride went from trigonal planar, flat, to something tetrahedral. Okay, that's where I'm going to end for this video, and we'll continue more next time.